Welcome back. In the last video we have seen Riemann-Lebesgue lemma, the property of a Fourier transform using the Riemann-Lebesgue lemma for periodic signal over finite time period. So, what we are looking for the Riemann-Lebesgue lemma for non-periodic signal, that is the signal over infinite time. So, that is our full real line f(x), x belongs to the full real line. We can also prove this by dominated convergence, some theorem. So, which is another version of Weierstrass-M test, which if you know, I think you know from calculus, Weierstrass-M test, sequence of functions converges to something uniformly. So, you try to look for this Weierstrass-M test, this is a similar version. So, I will try to give you that theorem without proof, and then we make use of that theorem and we will prove this Riemann-Lebesgue lemma, that is more convincing you. Okay, the proof will be more convincing if I try to use this theorem rather than giving earlier proof that is actually valid, but if you do not follow, this is much easier. So, we will try to give you this theorem without proof, a dominated convergence theorem. What it tells you is I choose some functions, okay, with parameter r. For every r you have some sequence of functions, be a family of functions, okay, be a family of functions, family of what kind of functions we choose, piecewise continuous functions, okay. And also absolutely integrable functions, piecewise absolutely integrable continuous functions. That is exactly what are those functions in your Fourier transform. What we do is, now if I have this condition f r of x, this quantity is less than or equal to some function, this is dominated by this function, all these functions for every r is dominated by this function g x that belongs for every x with a real number, and what you have is g is also absolutely integrable function, okay. So, dx is positive, is finite, okay, with this, and what we have is this limit f r of x as r goes to 0. This is actually f x pointwise convergence for every x belongs to the real. Suppose you have this limit, then what you have is a limit let me choose. So, this limit exists, r goes to 0, okay. So, now I try to integrate f r of x dx, okay. So, I think you should choose this g x, it is dominated by this, which is anyway positive. So, modulus of g x does not matter, so the g x means modulus or without modulus, because g is always positive. This means g is absolutely integrable function. So, in this case, so once you have this limit, the conclusion is this minus infinity to infinity, these are absolutely integrable functions, okay. If this is actually equal to what this theorem tells you is, you can allow this limit to go inside this integral. So, if I do this, this is what is the case, r goes to 0 f r of x dx, but this limit is given as f x dx. So, this is what it tells you, this dominated convergence. So, whenever you want to have a limit, you have a limit outside some integral, you want to pass this limit inside the integral, what you have to do is you just need to check whether your sequence of functions, those sequence of functions, whether they are dominated by some function which is absolutely integrable. If in such a case, you can just pass this limit inside, okay. We will often use this is a very useful result. So, you will try to if you do not understand this, if you have not seen this theorem, you try to understand this statement, you can use very often throughout throughout the course, many other courses is useful. So, try to use this, try to understand this statement and follow this, okay, use this whenever it is required. So, now we will try to use the Riemann-Lebesgue lemma again, another proof using this theorem. We will try to prove this Riemann-Lebesgue lemma. What we have proved in the last video. So, if f is f of x is absolutely or piecewise absolutely piecewise continuous and absolutely integrable functions. Function, then f cap of xi Fourier transform mod xi goes to infinity has to be 0. So, this is we will prove this way, very easy way. So, this proof will be more convincing for you. So, let me start with this f cap of xi, which is 1 by root 2 pi, and you have minus infinity to infinity f x e power minus I xi x dx. So, what is this? What I use right now is a small trick. Let me use u equal to x minus pi by xi. Let me choose such a variable. Then what happens? F cap of xi, I use this change of variable into this integral. So, left hand side will not change. So, I have this 1 by root 2 pi for every fixed xi. Xi is real number. So, once you have this, you see x in when you put minus infinity, this is a fixed number. So, you have minus infinity to infinity, dx is du now, okay, and you have e power minus I xi, x is u plus pi by xi, and you have f of x is u plus pi by xi. This is what you have. So, what is this one? This is actually equal to 1 by root 2 pi. So, e power minus I pi. So, what is this one? So, integral minus infinity to infinity f of u plus pi by xi. This is e power minus I xi u, and what you have is e power minus I xi into pi by xi, that is e power minus I pi, that is cos pi is minus 1. So, you have a minus 1. So, minus 1 comes out. So, you try to take the average of these two, sum of this and take half of that. So, you have f cap of xi, that is the trick you have. So, you have 1 by root 2 pi minus infinity to infinity, and you have 1 by 2, 1 by 2 this quantity plus this quantity divided by 2. So, and if you do that, f of u minus, when you are adding, because already minus sign. So, you have f of u plus pi by xi, okay, and you have this is same e power minus I xi u du. This is exactly what you have. Now, you try to take the modulus for this, you have a modulus, and this is less than or equal to 1 by So, now for this you try to apply both sides limit mod xi goes to infinity. If I apply this, mod xi goes to infinity. I want to pass this limit inside this integral. For that, I have to choose for different xi values. Xi is the parameter, like earlier in your theorem, r is the parameter, here xi is the parameter. So, if you look at this mod f of u minus f of u plus pi by xi, this quantity, first of all, f is absolutely integrable function. So, this quantity is also absolutely integrable function, and this is dominated with I choose this mod f of u plus mod f of u plus pi by xi, a simple inequality. So, this quantity is absolutely integrable function, implies this quantity itself is absolutely integrable, and now you have a function which is sum of these absolute values, that is also new function. This is your g, this is also absolutely integrable function, and what you have is a limit f of u minus f of u plus pi by xi as xi goes to infinity, both sides. Mod xi goes to infinity, this quantity is actually going to 0 for every u belongs to real line. It is clear, right. So, you can pass this limit, inside this integral. So, you have, that implies what you get is mod xi goes to infinity, f cap of xi is equal to 1 by 2 times square root of 2 pi, we can take minus infinity to infinity, f of u minus, so I can, this is the limit mod xi goes to infinity, I put this goes inside and you have f of u minus f of u plus pi by xi into e power minus I xi u du, right. So, this is what you have, but this goes to, this quantity goes to 0. Okay. So, once you have the modulus, you take this modulus inside, okay, and now you have the modulus here. So, take this modulus inside, what you get is 2 root 2 pi minus infinity to infinity, limit mod xi goes to infinity, the modulus I am putting inside of f of u minus f of u plus pi by xi, and then this into this modulus thing inside e power minus I xi u du. So, because of this modulus on into this, you can put this as 2 modulus and this modulus is 1. So, you have 1 modulus here, and this quantity is actually 0 for every. So, you have this is less than or equal to 0, that means positive quantity less than or equal to 0 means it has to be equal to 0. Okay. So, that is exactly what you want to show, limit mod xi goes to infinity, Fourier transform at extremes, both the extremes is going to 0, that is the meaning of this. Okay. This is the Riemann-Lebesgue lemma using this important theorem in calculus, that is dominated convergence theorem. So, if you have a sequence of functions and you want to, you know its limit and it converges to some function, and if you want to integrate these functions and pass the limit, and you can do this provided this one sufficient condition is this dominated convergence theorem, that tells you that these functions, sequence of functions are dominated by certain thing which is whose integral value is finite. If such a thing it is there, then you have this, you can pass this limit inside this integral. So, using that you proved this Riemann-Lebesgue lemma. We will try to prove one more small property. Before we will try to prove this, I think it's this is the useful thing. So, let me do this one. So, let if f is, if f of x is absolutely integrable function, in minus infinity to infinity and piecewise function and piecewise continuous function in this, okay, in this in full R minus infinity to infinity, then f cap of xi is a continuous function, Again this property also you can prove, this Fourier transform is a continuous function always as a function of xi belongs to the full real line. So, what do you do to prove this this thing? We have to prove f cap of xi plus some h you take minus f cap of xi. Now, if you take allow this h goes to 0 both sides, this you want to show that this is equal to 0. Okay. So, by definition this is actually equal to h goes to 0, this is the proof of this property. Okay. So, h goes to 0, f cap is 1 by root 2 pi and this will be minus infinity to infinity f of x, which is common in both the things, and what you get is e power minus I xi plus h here x minus e power minus I xi x dx. This is what you have. This is equal to limit h goes to 0 1 by 2 pi this e power minus I hx, you can take it out, okay, e power minus fx into e power minus I xi x, that is common. What you have is e power minus I hx minus 1 into dx. Now, you can pass this limit because this is the limit h goes to 0, you have this function. So, clearly e power minus I hx minus 1 limit h goes to 0 is equal to 0, and these are dominated by So, what we do is if you choose like this, you have to show that this is dominated by some function which is maybe modulus of this plus 1. If you choose 2 which is not integrable, what you do is you try to choose fx, any fx, this is what is the case, this is true for every x belongs to R. Then and what you have is now fx times e power minus I hx minus 1, this is dominated by fx plus fx, okay, modulus of this. This is because f is absolutely integrable function. So, you have integral of this is also, this is a 2 times f which is 2 times mod fx which is absolutely integrable function. So, you have dominated by this. Now, I can pass this limit inside. So, what you get is a limit h goes to 0. So, that is 1 by 2 pi minus infinity to infinity. If you pass this limit h goes to 0 fx e power minus I xi x e power minus I hx minus 1 dx. This is nothing to do with h, this limit you pass it here, that is 0. Okay. So, that means what you have proved is this limit equal to 0, that means f cap of xi is continuous function, implies f cap of xi is a continuous function. In minus infinity to infinity. We may use this some places. So, if we, it is always better to know this good result. So, f is f cap, the Fourier transform is always continuous function. F need not be a continuous function, but it is a, but this Fourier transform it smoothens. So, basically it makes it continuous. Transformation, Fourier transformation makes it a continuous function, non-continuous function to a continuous function. Now, we will try to prove this basic result, that is Fourier integral theorem, which we will prove rigorously. With this once we prove this result, Fourier integral theorem, whatever we have defined as a Fourier transform and its inverse transform are legitimate. Earlier we have proved this Fourier integral theorem in an intuitive way, that is to explain, that tells you that Fourier series, that is Fourier transform of a periodic signal is connected with the Fourier transform of non-periodic signal. So, what we have done there is we have taken the Fourier transform of periodic signal, that is a Fourier series, and its inverse transformation is Fourier series. Okay. That Fourier series, through Fourier series we try to using the Fourier coefficients and the Fourier series, we try to show that it converges the final Fourier integral theorem we have proved by allowing that finite interval, that is from minus L by 2 to L by 2. I allowed L goes to infinity finally. So, periodic signal becomes non-periodic signal, and then that is our full real line, and also you have seen the what is the limit of that as L goes to infinity. In an intuitive way, in more formal way, we have derived this Fourier integral theorem. So, that is it is not rigorous proof, but that gives you the idea that it is the Fourier series, the finite signal Fourier transform and this infinite Fourier signal over infinite time, there is minus infinity infinity non-periodic signal Fourier transform is also they are connected. But this we will try to prove mathematically in a more rigorous way. So let us choose if f of x is an absolutely integrable function. And smooth piecewise smooth function. Piecewise smooth means n derivatives you take, it is n derivatives are it is n times different, any number of times it is differentiable except at finitely many points it is the derivative is piecewise continuous function. That means you have only finitely many only jump discontinuities are allowed for any n derivatives of such function f x. Piecewise smooth on R. What we require here is only piecewise smooth, only f double dash is piecewise smooth function, is piecewise continuous function, piecewise continuous function. That is the meaning of smooth here. We use only this one f2 derivatives. In general definition of piecewise smooth, if I recall, any derivative it is infinitely differentiable, any number of times you can differentiate, every time that any nth derivative is piecewise continuous function. So that is the meaning of, so let us use this, we choose this smooth function piecewise smooth on R. In minus infinity infinity, then what you have is this limit, I write like this, or 1 by root 2 pi minus infinity to minus r to r f cap of xi, this we know already, okay, Fourier transform that we defined dx, which is equal to 1 by 2 pi. Now this is, as if you allow r goes to infinity, minus infinity infinity, root 2 pi I have actually, and inside this is also 1 by root 2 pi, that if I bring it outside 1 by 2 pi, and this is a definition of Fourier transform. If I write here, you have f x e power minus I xi x, okay, dx, this is d xi, okay, this is what you want, and you have e power minus plus I xi x d xi. So I will try to use this different notation. So let us use d y, so that you have dy here. So this is your dy, this is the dummy variable. So this is exactly your Fourier integral theorem. This is equal to half of f x plus f x minus. If it is discontinuous, there is a jump. If it is a discontinuous, there is a jump here. So this half of that jump, that is the meaning of this. If it is here, both sides limits are same, so half of that is actually the value. So in any case, this is what is true for every x belongs to R. R is minus infinity to infinity. That is the meaning. So this is exactly, we will try to prove this in a more rigorous way now. So proof, let me start the proof. So we first observe that integral minus r to r e power I xi x minus y d xi. What is this integral? What is this one? So this you try to integrate, you get divided by I x minus y and e power I xi x minus y, and then xi equal to minus r to xi equal to r. If you apply this, you have 1 by, so minus I by, or rather keep I times x minus y e power I xi is r x minus y minus e power minus I r x minus y divided by 1 over this. That is exactly what you have. Okay. So, this is same as what is this one? This is 2 times sin r x minus y divided by 2I. So, 2I goes. So, what you get is the 2 times of that divided by x minus y. So, this is the meaning. So, first you observe that this is the result. Now, what I do is I try to take this this part in your statement 1 by root 2 pi minus r to r f cap of xi e power I xi x d xi. So, this is equal to, and I will replace f cap by this Fourier transform definition. So, that you get 2 pi minus r to r, and this is going to be minus infinity to infinity f x, or let me write f y e power I xi x minus y e power I xi minus I xi y I combined with this. So, to write that into d xi dy and then d xi. So, you can, because this quantity is absolutely integrable, integrand is absolutely integrable, and you have already seen. So, this is as a function of x y y and xi, as a function of y and xi. Xi is anyway between minus r to r, which is a finite interval. This is the integrable function. This the double integral is finite. So, all you can do the integration, you can do order of integration, you can change, and you can write this as minus r to r and minus or rather, if you change the order of integration there, because there are 2 different integrals domains. So, if you change the order of integration, it is going to be minus r to r f y e power I xi x minus y d xi and dy. So, this you do integration, f y you can write here. So, you remove here, and if you try to do this integral, that is exactly what we use here. So, you substitute there. So, you get 1 by 2 pi minus infinity to infinity f of y 2 times. So, 2 comes out. So, you have 2 comes out. So, 2 goes 1 by pi to sin r times x minus y divided by x minus y into dy. That is what you have. Okay. So, if I use x minus y equal to t, okay, then what happens to y? Y is x minus t. Okay. So, 1 by pi, just do the change of variable in this. If I do this, sin r t by t, and you get f of y is x minus t dt, dy is dt. I have a minus dt, dy is minus dt, x is fixed. Okay. So, you have x is fixed here. So, and then what happens to your limits when y equal to minus infinity is going to be plus infinity, t is plus infinity, and this is going to be minus infinity. This minus if you remove, you can interchange. Okay. You can interchange the limits with that minus. So, this is what you have, and now I can rewrite this as this is exactly definition of my 1 by pi times what is this is if you look at it, this is exactly your convolution product of let me use 1 by pi times convolution product of f star G is some G of x, where G of x is equal to what is your G of x is sin r. So, G depending on r, let me call this G r, okay, okay, G r t by t. This is a function of x I wrote, so I have G r x by x. Okay. So, you have like this. This is exactly your convolution product. I will rewrite this as 1 by pi times f star of, instead of writing this way, what I write is I write G of 1 by r of x, where G of 1 by r of x is 1 by r times G of that is rather sin r times sin r x, I write x divided by 1 by r divided by x, okay, x into 1 by r. So, with this 1 by r, if I write, this is exactly what you have, right. This is r x. So, you try to write sin r x by r x into r, okay. So, if you want this one, you can rewrite here also. So, you can write sin r x divided by r x. So, I have to multiply r. So, this will give me, I can rewrite 1 divided by 1 by r times sin x divided by 1 by r divided by x divided by 1 by r. That is how you are writing. So, that way if you rewrite, so you can write G, what is your G 1 by r is G 1 by r is 1 divided by 1 by r times this is x divided by 1 by r. So, that is, so you can rewrite this as some function. If you define G of x is sin x by x, so you can write G of x divided by 1 by r, where with G of x is sin x by x. So, this quantity I replace sin x by x. So, in the place of x I put x divided by 1 by r, G of 1 by r, okay. So, this way of writing you have some advantage. So, we will use that one and we will try to prove. So, eventually what we do is I allow r goes to infinity. So, that is going to be G of 0, I allow eventually r goes to infinity. Another important thing that we need is this integral 0 to infinity sin r x by x dx. This is because this is the even function, this is even function. Because of this even function, minus infinity to infinity of this is actually 2 times 0 to infinity sin r x by x dx, or 2 times minus infinity to 0. So, that means to say both are same. So, 0 to infinity, this is same as minus infinity to 0, okay, whose value is actually equal to pi by 2 if r is positive, right, which is the case. R is anyway positive. So, what is r? So, r I choose minus r to r going to, so r is always positive. So, because r is positive, this quantity is pi by 2. So, this we note this, that these two integrals we may use. eventually. Okay. So, having done this, now I can take the left hand side minus the limit. So, what we have, this is the left hand side, and this minus, and what you look for is this one. So, this minus this, if I take, I look at its estimate and I show that there is going to be 0 as r goes to infinity. So, let me use 1 by root 2 pi minus r to r e power I xi x f cap of xi d xi minus half times f x plus f x minus. Now, this is actually equal to, so if you now put this, first one is 1 by pi, first one is this one is 1 by pi, right. So, 1 by pi, first term is 1 by pi minus infinity to infinity sin r y by y f of x minus y dy. The other one is minus, you can because I use this, I try to use this one, these two integrals, I use it here. So, how do I use this? I multiply pi by 2, or rather 2 by pi into half f x plus, for this x plus I will try to use, and because I multiplied this 2 by pi, I have to multiply, I multiply pi by 2. So, 2 pi pi into pi by 2. So, that pi by 2 I replace this integral. So, 0 to infinity sin r y by y dy. For the other one, again you do the same way, 2 by pi times half f x minus into minus infinity to 0 sin r y by y dy. So, this is what is 2 goes here both the places, and what you get is 1 by pi. Now, what you have is, now you try to split this into 2 parts, 0 to infinity, first I try to use 0 to infinity, you rewrite this as the 2 parts, 0 to infinity and minus infinity to 0. 0 to infinity, if you write, and this sin r y is common, sin r y by y is common, and what you have is f of x minus y from this, and here minus f x plus from 0 to infinity into dy. I combine these 2 parts, first 0 to infinity part here and this integral. If you do, this is what is the result, plus minus infinity to 0, again you do the same thing, sin r y by y, r is y is common, and what you get is here f of x minus y, and here minus, what you get is f x minus dy. This is what you have. So, this is exactly you have now. What I do, I will try to take this one. So, I will look at this one, this integral, and we will try to estimate these integrals as r goes to infinity, what happens to these 2 integrals. We will try to this. Evlo neram achupa? Okay, okay. So, pandalam. So, we will try to look at this integral, and I also try to look at this integral, and we will see eventually as r goes to infinity what happens to, I am trying to prove that this r goes to infinity, each of these will go to 0. Okay. So, how do I see this? We will look at this integral first, and this is a similar way you can do this. Okay. So, let me do only one. So, we will consider 0 to infinity sin r y by y f x minus y minus f x plus dy. This is equal to, so I split this into again some big number, some number you take for any k, for any k positive, I can split this into 0 to k, because this is a 0 to k plus k to infinity. I can always do this, sin r y by y f x minus y minus f x plus dy. Okay. This is I can always do. If I choose k is greater than or equal to 1, what you have is this is from k to infinity, because this is more than 1 to infinity. So, if k equal to 1 to infinity, sin r y by y f of x minus y dy, this quantity this is always less than or equal to, because if k is bigger than 1, sin is sin of r y is always less than or equal to 1 by y, if y is in k to infinity, if k is bigger than 1 by y is always less than 1. So, in that way you have k to infinity modulus of f of x minus y dy, and what you have is the other one is simply what happens to your k to infinity sin r y by y f x plus dy. This is actually equal to f x plus comes out, and this is from k to infinity. So, try to put r y as a t variable. Okay. So, then what you get is sin t by t. So, what I did is r y equal to t. So, you get r dy is dt by r. So, you have 1 by r dt by r, and y is t by r. T by r is r comes up. Okay. So, r goes. So, you do not have to write anything here, sin t by t dt, and what happens when k. So, you get t is from k r to infinity. So, this is what you have. So, if you have k is greater than or equal to 1, this is actually true for any k, this is true, this quantity, this integral, but this integral is valid only for k greater than 1. So, for k greater than or equal to 1, both the things we use. Okay. Now, if you can see, if I allow k goes to infinity, k goes to infinity, what happens? If I allow k goes to infinity, this is going to be 0 and this is also going to be 0. So, that means this is also going to be 0. Okay. So, as k goes to infinity, clearly this is going to be, as if I take k bigger, this quantity again that is actually kind of trivial thing. Okay. So, this quantity you can ignore for bigger k values, this can be made small as possible for any r. Okay. So, that is the reason we have done these two. So, these two quantities you can easily see separately, that these two, this k to infinity integral is actually you can make as small as possible for bigger k values, as long as r is positive, okay, which is anyway positive. And we look at the other part, this k to infinity. So, let me write as k to infinity sin r y by y f of x minus y minus f of x plus this quantity dy, this goes to 0 as k goes to infinity. That is what is the meaning of these two calculations. Okay. Now, that is not the thing. So, we look at this 0 to k. So, such a big k value if I choose, and the second integral is nullified, and the only first integral is the actual value. So, if I choose such a big k value, so for such a big k, what you have is sin r y by y f of x minus y minus f of x x plus. Is x plus or x minus? I think it is x minus, right. I combine it with I think I have chosen, does not matter, I think x plus only, x plus. Okay. This is x plus dy. What happens to this? This is equal to 0 to k. Now, I can rewrite the sin r y by y, earlier we have defined as okay. So, 0 to k, you write this as sin r y times this you rewrite. So, this f of x where f of x minus y minus f of x plus divided by y as some g of y. You try to define it like that. If you do this, you have this g of y dy. Okay. So, what is this one? This is actually equal to, this is between, now think of g as a function which is function y belongs to 0 to k. So, which is a periodic signal, and because f is absolutely integrable function and 1 by y is between 0 to k. Okay. And you can see that at 0 it is well defined, g is the function. You have to worry about see g is f is a piecewise continuous function. So, this numerator is piecewise continuous function except at x y equal to 0. So, in this 0 to k interval, g of y is piecewise continuous, and it is piecewise smooth function rather, okay, piecewise continuous, piecewise or piecewise smooth function you can think of, because that is what we have chosen in the hypothesis. F is a piecewise smooth function. So, on this interval, finite interval, f is a piecewise function except at y equal to 0. At y equal to 0, what happens? So, we look at this limit y goes to 0, what happens to this x minus y minus f x plus divided by y. So, this is actually equal to what is this value? This value is actually going to f x as y goes to 0, what happens? G y, this means this is x plus as y goes to 0, this is actually is equal to derivative of df of dx, that is f dash at x plus side, you can think of that. Okay. So, that we know that this is f dash is piecewise smooth, and piecewise smooth means f dash is piecewise smooth means it has only jumps even at 0. At 0 it cannot have infinite jump, that means this is a finite, this limit exists as a function, a derivative. So, this is finite, implies g of y is piecewise smooth function. That means you can write this, you can think of this as integral 0 to k g of y. Now, I can rewrite this as sin 2y as e power I xi I or some so rather sin I r y minus e power minus I r y divided by 2I into dy. So, this one first term if you use 1 by 2I comes out, first term is actually g cap of that is Fourier transform. So, Fourier coefficient. So, here let me use same notation g cap or Cn, okay, Cn of minus C rather how do I put it, C r of this is Cr rather, Cr is the coefficient here minus C minus r. Okay. This is C minus r and this is Cr minus this is Cr. Okay. So, if I take this up minus I, so you make it plus, so you have this is Cr and this is C minus r, this is how it is, okay, both are same. So, you can easily see that this quantity 0 to k integral is actually equal to this. Now, you can easily see, now what we have to show is we have seen that g is a piecewise smooth function, g is bounded at 0. So, that is a piecewise smooth function in this interval, k is sufficiently big, so that I can make this quantity make less than epsilon. What happens 0 to k, this part 0 to k integral will be is this one. Now, if I allow as for sufficiently for large r, that is what you want, r goes to infinity, this quantity can be made less than epsilon. Okay. So, this can be made less than epsilon. Okay. So, CR minus C minus R by Riemann-Lebesgue lemma, this can be made less than into I by 2 can be made less than epsilon for large R. That means as R goes to infinity, this integral 0 to k sin Ry by y f of x minus y minus f of x plus dy goes to 0. That is the meaning. Okay. Because this I can make this 0 k to infinity for sufficiently large k, first I made this is less than epsilon. Okay. For some big k, by choosing some big k, I can make this less than epsilon. So, I have that 1 epsilon I have. Now, for 0 to k integral, now this can be made less than epsilon. So, you have 2 epsilon. So, that the epsilon is arbitrary, that is the meaning is. So, for large r, that is as r goes to infinity, this overall 0 to k this goes to 0. Okay. For large, so k is already you have chosen such a big value. So, that means as r goes to infinity, k is already goes to infinity. Okay. So, in that way, so you do not write like this. So, what we see is for large r, this quantity can be made less than epsilon, that is what we want to put it. So, that means for sufficiently big k, this quantity finally can be made less than epsilon. Okay. So, this means what I have is 0 to infinity sin Ry by y f of x minus y minus f of x plus dy can be made less than 2 epsilon. Okay. For large r. So, for large r means for r is bigger than some capital R, okay, which is positive, for r is bigger than some r. So, this is exactly the meaning of limit r goes to 0, this quantity sin Ry by y f of x minus y minus f of x plus dy is equal to 0. So, that is what is the meaning of this, r goes to infinity. So, what we have proved here is this quantity, this integral is going to 0 as r goes to infinity, and similarly same way, same technique, you can show that this also goes to 0 as r goes to infinity. So, if I allow this r goes to infinity, what you have is this total thing will be with r goes to infinity, this is r goes to infinity. Now, what we have proved just now is this part is 0, and also you can prove the same way this part is also 0. Okay. So, that means limit of this is same as this quantity, because it is a fixed number. Okay. So, that means limit of this is equal to this one. This is exactly what you want to show in your Fourier integral theorem. So, this is exactly true. So, what we have proved is the Fourier integral theorem in a rigorous way without having without any issue, everything is legitimate here. We just made use of some of the ideas, some of the convolution product also we have used, though we have not used this. I have not used this. So, we have I tried to put it this, I thought of using, but I have not used, and anyway. So, this is does not matter. So, from here we just in a more elementary way we try to show that Fourier integral theorem. Okay. So, now it is legitimate to define from this you can define what is the Fourier transform and its inverse transform the way we have defined, and then we have seen a lot of properties of the Fourier transform. Now, in the next video we will try to apply this Fourier transform and inverse transforms to solve some partial differential equations or boundary value problems of for partial differential equations or differential equations. Okay. We will try to prove, we will try to define those boundary value problems and then try to solve by this Fourier transform technique. We will see the application of, basically we see the applications of Fourier transform and in the next few videos. Thank you very much.